going backwards to limits in order to understand where the derivative of trig functions come from. We're going to go back to the idea of limits with trig functions. So it is important to recall that the limit as x approaches 0 of sine x is 0. You get that via direct substitution. Sine of 0 is 0. Cosine of 0 is 1. Tangent of 0 is 0. And then we have our trickier sine and cosine limits. It's important to recall that the limit as t goes to 0 of sine t over t is 1. That changes if there are values inside the sign and in the denominator, as well as 1 minus cosine t over t equaling 0. So we're not going to reinvestigate these. We kind of already did that. We are going to find the limit of the trig function. So it says find the limit as x goes to 0 of sine 5x over x. So we know that in order to find that limit, we must have a 5 in the denominator. So in order to create a 5 in the denominator, we need to multiply by 5 over 5. Creating the limit as x approaches 0 of 5 sine 5x over 5x. So now this is like sine t over t, except for it's sine 5x over 5x. So that's always equal to 1. So the limit as x approaches 0 of a constant is equal to the constant times 1. Therefore, this limit is equal to 5. The limit as x approaches 0 of sine 4 of 7x over 4x. So in this case, I need sine 7x to be over a 7, not a 4. So you need to recall that in properties of limits, you can bring a constant out. So I could bring the 1/4 out in front, but that still leaves me with an x missing a 7. So I need to multiply by 7 over 7. Again, that's like multiplying by 1. So you get 7/4, because you can bring any constant in front of a limit, times the limit as x approaches 0 of sine 7x now over 7x. When top and bottom match, that's equal to 1. So we get 7/4 times 1, which is 7/4. There is, I moved it here. Okay, now we have sine 5x over sine 7x. The reciprocal of the limit was also true. We proved that back in chapter 2. So now it's kind of nice to think about this problem as the limit as x approaches 0 of sine 5x times the limit as x approaches 0 of 1 over sine 7x, which means I need an x here and an x there. So I'm going to multiply by x over x. So now we have our x's, but over on the left, I still need a 5, and on the right, I need a 7. So I could either multiply by 35 over 35, or by 5 over 5 and 7 over 7. But again, not breaking any laws of algebra when I multiply by the number over the number. So I get 5 limit as x approaches 0 of sine 5x over 5x times 7 limit x approaches 0 of 1/7 of 7x over sine 7x. So you get 5 times 1 times 1/7 times 1, or 5/7. Yes. Because I put 1x with the 7x and I put 1 with the 5x. Okay, let's talk about cosine. So you have cosine 7x over cosine 4x. Remember that the very first thing you are ever supposed to do when you have a limit is to substitute. So you get cosine of 7 times 4 over cosine of 4 times 0, which really is like the cosine of 0 over the cosine of 0. And recall that the cosine of 0 is 1. So you get 1 over 1, or 1. So do not fall for the trap and try to write the answer as 7/4 because you get so comfortable with the sign being the values of the fractions. would be 0 over 0, which is the indeterminate form. And limit as x approaches 0 of tan 2x. Remember that tangent is really sine over cosine. So that's like the sine of 2 times 0 over the cosine of 2 times 0, which is like the sine of 0 over the cosine of 0, which is 0 over 1, which is 0. So there's our little trig review of limits. Now what we want to do is take that review and accelerate it to look at derivatives. So we're going to take that review and we're going to accelerate it to look at derivatives. So in order to find the derivative of trig functions, you have to know the values of their limits involving trig functions, reviewing your trig identities, which is what we did in that trigonometric packet. That's why we did that after our quiz before today. Reviewing all of those trig identities that are so crucial, going through SOHCAHTOA, understanding radians and degrees. We are going to investigate those 4 important limits. So again, we already talked about it, the limit as h approaches 0 of sine x. Well, do you have an h in that problem? So you have the limit as h approaches 0 of sine x. So this is super critical to understand. Is there an h in that problem? No, so there's nowhere to plug 0 in, right? So the limit as h approaches 0 of sine x is sine x. The limit as h approaches 0 of sine x is sine x. The limit as h approaches 0 of cosine x, lo and behold, then, is cosine x. So then the limit as h approaches 0 of sine h over h is less obvious. We actually discussed and found what it was using the squeeze theorem way back in chapter 2. So at this point, because we've proven it via the squeeze theorem, we know that the sine of h over h is always 1. So we know that based on the squeeze theorem, the sine of h over h is always 1. You could graph that and see that. And then it says we can deduce the value of the remaining limit. So again, limit as h approaches 0 of cosine h minus 1 all over h. Well, in order to simplify this, we need trig identities. If you want to know how or why this is really 0. So if you wanted to know how or why this is really 0, you'd look at the beginning right here and say that that looks a lot like half of the difference of squares formula. So you could use the complex conjugate. And multiply by the other half of the difference of squares formula. Giving the limit as h approaches 0 of cosine squared h. The inner will cancel. Minus 1 all over h cosine h plus 1. Well, now, what do you know about your trig identities? Well, we need to recall from trig identity days that sine squared plus cosine squared is equal to 1. So flip-flop some stuff up in there, and you get cosine squared h minus 1 is equal to negative sine squared h. Because you'd subtract the 1 and subtract the sine squared. So let's go ahead and substitute that in. And what could I do to my numerator? Sine squared h is really the same as, sorry. Isn't sine squared h really the same as sine h times sine h? You believe that, right? It's like x times x. What do you know about the limit of sine h over h? It's 1. So really I could rewrite this right? So you separate at the top, separate the bottom. Remember, I'm not adding or subtracting. I'm multiplying all of this. So if I just moved out that middle limit, the multiplication hasn't changed. We said sine h over h is 1. So this limit becomes 1. At this point, can I plug in 0 to the top and bottom of the second part? The sine of 0 is 0. The cosine of 0 is 1. So now my denominator is not 0. 1 plus 1 is 2. So I get 1 times 0 over 2, which is 0. against the rule on the previous page. We love to know the how and why and where in mathematics. We like to know the how, the why, and where in mathematics. Nobody likes to ever believe why something is the way it is. You want to be shown. So, at this point, we've talked a ton about limits. If you go back to our past lessons when we talked about limits, the next move was to talk about the definition of the derivative limit. So let's use the definition of the derivative. I know you guys all thought it was gone. To find the derivative of sine x. So recall that the definition of the derivative is limit as h approaches 0 of sine. We'll just give the basic definition to start. Limit as h approaches 0 of f of x plus h minus f of x all over h. And in this case, my f of x is sine x. In this case, my f of x is sine x. So, the proof becomes the limit as h approaches 0 of sine x plus h minus sine x all over h. And this is why number 7 existed on that packet, because you need to know how to rewrite the sine of x plus h. So the rule is that if you have a sum of problems, it's the sine of the first times cosine of the second plus the sine of the second times cosine of the first minus the sine of x all over h. Just put in the number it belonged in. Thank you, dear. Set it there then. That one doesn't work now. Thank you. Okay. So what do you know about a denominator of h? Well, we know if it's a single denominator, I can split it up amongst terms, right? We also know that we can rearrange our terms. So looking at this problem, I want to get my sine x's near each other. Remember, a limit can be added where you can put the plus sign between multiple limits. If you didn't put your limit in front of there, that's okay. What do you notice, though, happening right here? Yeah. Can you do anything with cosine x? Does the x variable match the limit? So the limit as h approaches 0 of sine h over h times cosine x. Well, cosine x is like a constant. So that part is equal to cosine x. That part of this is equal to cosine x. What can I do over here? What can I do with sine x? I can factor it out. Fantastic. And sine x is like a constant because we're looking at the limit of h. Oh man, what identity is this? Limit as h approaches 0 of cosine h minus 1 over h is equal to 0. 0 times sine x is equal to, so goodbye. That means I am left with cosine x. So lo and behold, the derivative of sine x is cosine x. And you have just proven that. The derivative of sine x is cosine x. Forever and ever beyond this, you can now say that the derivative of sine x is cosine x. Yes. Where did it what? It's part of the definition of the limit as h approaches 0. Like if you look up on your page, the limit is h approaches 0 of cosine h minus 1 all over h equals 0. So minus 1 is part of it. Who wants to prove the derivative of cosine using limits? You guys seem super thrilled today. No one? Everyone? You do. So yeah, that's what we're proving. That the derivative of cosine x is equal to the limit as h approaches 0 of cosine x plus h minus cosine x all over h. So going back to, again, that page that we found our derivatives for, and looking at example number 7, and now we're looking at part B, the cosine of x plus h. Becomes the cosine of x, cosine of h, plus the sine of x, sine of h, minus the cosine of x, all over h. So what do you think we're going to do again? Sorry, that should be a minus. It's always the opposite for cosine. Should have been a minus. When you add the cosines, it's the opposite. We're going to rearrange our terms to get the cosine, and I think it might even be wrong on your other handout. It's always the opposite for cosines. We're going to rearrange our terms to get the cosine x's together. And recall that cosine x and sine x are like constants. Therefore, they can come in front of the limits. And we end up with cosine x times 0 minus the sine of x times 1. Which means that the derivative of cosine x is negative sine x. The derivative of cosine x is negative sine x. Yes, maybe. There you go. Okay, which leads to our conclusion for the derivative of all the trig functions. Leads to the conclusion for the derivative of all the trig functions. Now you'll notice that I've underlined in black all of the trig derivatives that have a negative derivative. The derivative of all the trig functions that start with C have negative derivatives. So you're just filling this in at the bottom of that page. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Cosecant's derivative is negative cosecant cotangent. And derivative of secant is secant tan. It's also at the top of your next page. So again, I personally like things to be nice and neat, so it's at the top of your next page as well. Okay, so A couple years ago, we were discussing like easier ways to memorize these. So if you take secant, for example, and you go for its derivative to the right, basically, the derivative of secant is secant tan. Conversely, if you start with tangent, its derivative is to the left. It's secant secant. So the derivative of tan is secant secant or secant squared. Derivative of secant is secant tan. So they like to remember like SST and CCC. And you can just kind of think of it as going in either direction from the outside. Again, that was just another student's thought process a couple years ago for a way to remember it. Secant is secant tan. Tan is secant secant. So you can go in either direction. Okay, so let's find the following derivative. You have x squared times sine x. So this is why our rules were so important. Y prime is equal to the first times derivative of the second. Derivative of sine is cosine plus the second times derivative of the first. So it's very important to make sure we are aware of where one function ends and another begins. So that 2x and the sine x don't get multiplied together. This does not become sine 2x squared. It becomes x squared cosine x plus 2x sine x. Because the x on sine is part of its angle. So that's separate from the actual function itself. So like there's these imaginary parentheses around the angles of trig functions. If you need them, you can write them. But again, it's important to know it's not the sine of 2x squared. It's 2x sine x. Okay, you have secant x over 1 plus tan x, which means we need the quotient rule. It means you need the quotient rule. So it's Hody high times the derivative of secant minus high do. Derivative of 1 is 0. Derivative of tan is secant squared. All over. Denominator squared. To clean it up, algebraically, you could distribute the secant x tan x to 1 and tan. What do you notice about each term in the numerator? Yeah, they all have a secant, so we can factor that out. We previously talked about trig identities. So we talked about sine squared x plus cosine squared x is equal to 1. What are the trig identities for secant and tangent? Well, the tangent squared x plus 1 is equal to secant squared x So that's not the same as the denominator, so be careful. You can, however, say that tan squared minus secant squared is equal to -1. And what do we have right here? So we can say that the secant of x, tan x minus 1, all over 1 plus tan x squared. Bless you. And then last two examples, you have y prime equals first times derivative of the second. So derivative of cosine is negative sine plus the second times derivative of first minus the derivative of cotangent, which is negative cosecant squared. Clean it up, and you get negative x sine x plus cosine x plus cosecant squared x. There are not times, and there are times where you can use trig identities. In this case, there's no trig identity for a sine or a cosine. Using the trig identity for cosecant squared would not help because it would just give me a cotangent. So we are done. And then example 4, y prime. So once again, you have 6 cosine x plus 4 cosecant x. 6 times derivative of cosine is negative sine plus cosine times derivative of 6. Well, derivative of a constant is 0. Plus 4, derivative of cosecant, negative cosecant cotangent, plus cosecant times derivative of 4, which is 0 also. So when you have a coefficient in front of a trig function, you don't really need the product rule because it is just a coefficient. If it was a coefficient in a variable, then you need the product rule. So what I'm doing here in this example is showing you how this is just a coefficient and not a function. If you did the product rule, you will see not a big deal. It zeroes out. So we get negative 6 sine x minus 4 cosecant cotangent. Make sure you put your x after the cosecant and after the cotangent. Okay, you're on page 146. We're actually changing this. What did I write? 146, 174.